What's up guys, this is Masi. Welcome to another video. In this video I want to talk about first order rate law. As you remember and as you saw in previous videos, when we are talking about rate of reaction, we can model it as change of concentration of reactant with respect to time, and we need to have the negative sign behind it to make it positive. But if you are dealing with changing concentration of product with respect to time, we don't need to put the negative sign there. That's going to be equal to K times the concentration of reactant to the power of N. If N equals to 1, it means that we are dealing with first order reaction. It means that reaction rate is proportional to the concentration of the reactant. So rate of change of concentration of A with respect to time is going to be equal to K times concentration of A. So here we have square bracket, meaning that we are dealing with molar concentration. On the other hand, we have K. K is reaction rate constant or rate constant, which is changing only with temperature. Now if you integrate this equation, you're going to end up having this integrated form. Ln of A. A means that the final concentration or the concentration at time t equals to negative kT plus ln of A naught. It means the ln of initial concentration in terms of mole per liter. That's going to be the integrated form after integration from the original equation. And if we plot ln A with respect to time, we're going to end up having a straight line, which is going to be equal to y equals to mx plus b. M is the slope, is equals to negative k, and b, y-intercept, equals to ln A naught. So the y-intercept is ln A naught and the slope is negative k. So when you move this ln A naught, if you move it to the left hand side, it's going to be ln A minus ln A naught equals to negative kT. And if you multiply both sides by negative, it's going to be ln A naught minus ln A equals to positive kT. Then you can say ln A naught minus ln A equals to ln A naught over A. That's one of the properties of ln function. Now that's exactly what you have in here. So from this expression you can end up having this expression, which is ln of initial concentration of A divided by final concentration of A equals to K times T. So with this relationship we can find out the K. If we have others, we can estimate the final concentration if we have the time, or if we have the final concentration we can find out the time. And then since it's ln, this expression equals to kT, we can say A naught over A equals to E to the power of kT. Or you can flip both sides and make it final concentration divided by A naught equals to E to the power of negative kT. And then you multiply both sides by initial concentration of A and you end up having this expression. So these are different expressions you can have for first order rate law. Let's see some examples. The first example, it says the initial concentration of the reactant is a first order reaction is 1.5 molar, which is mole per liter. So A naught is 1.5. The rate constant K equals to 0.05, 1 over minute, or minute to the power of negative 1. Part A, it says what will be the concentration after 1 hour. So K is in terms of 1 over minute. It means the time we need to convert 1 hour to minute. So 1 hour times 60 minutes per hour. These two cancel out. Is going to be 16 minutes. So we just put it in the formula. It's going to be A equals to A naught times e to the power of negative kt. That's what we had in previous page. So A will be equal to 1.5 times e to the power of negative 0.05 times time, which is going to be 60 minutes. So A is going to be 1.5 e to the power of 0.05 times 60 is going to be 3. So that's 1.5 times e to the power of negative 3. That is going to give me 0.074 mole per liter, or molar. That's going to be the final concentration after 1 hour. So that's the answer to part A. Part B, it says, how long will it take the concentration to be reduced to 0.8? So we again write the same formula, or we can write it in this form, doesn't matter. So I'm going to say ln of A naught over A equals to K times T. So it's going to be ln initial concentration 1.5, final concentration is 0.074 equals to K, which is 0.05 times T. So 1.5 divided by 0.074, then you can say ln 20.27. That's going to be ln, it's going to be actually 3.009 equals to 0.05 T. So T will be 3.009 over 0.05. That's going to give me around 60 minutes or 1 hour. So it's going to be roughly 60 minutes. The concentration is going to reduce to 0.8 molar. So in the first part, we had time and we calculated the final concentration. In the second part, we had the final concentration and we calculated the time. Let's see another example. At 1000 degrees Celsius, cyclobutane C4H8 decomposes in a first order reaction with the very high rate constant of 87 per second. So K is 87 per second, or you can write it as 1 over second, to 2 molecules of ethylene C2H4. If the initial butadiene concentration is 2 molar, which means that initial concentration is 2, what is the concentration after 0.01 seconds? So what is going to be the final concentration when time is 0.01 second? So we use the same formula. A equals to A naught times e to the power of negative kt, which means that A equals to A naught initial concentration is given is 2 to the power times e to the power of negative k, 87 times 0.01. So A will be e to the power of negative 87 times 2, that will be 0.8379, or we can say approximately 0.84 mole per liter. That's going to be the final concentration after 0.01 seconds. That's why it says the K value is really high. So it means that the reaction rate is fast. All of a sudden, in 0.01 seconds, the concentration reduced from 2 to all the way to 0.84. Let's do the part B. In part B, it says what fraction of C4H8 has decomposed in this time? What fraction? It means that A divided by A naught is going to be 0.84 divided by 2. It's going to be almost 0.42. It means that 58% of cyclobutane has decomposed. That's going to be the answer to the part B. Let's see another example. In a first order decomposition reaction, 50% of a compound decomposes in 10.5 minutes. So it means that the final concentration over initial concentration is going to be 0.5 because 50% is already consumed. In how long? In 10.5 minutes. What is the rate constant? So what is the value of K? Let's do the part A first. So we're going to say A naught over A, which is going to be equal to e to the power of kt. Or you can say ln of A naught over A equals to K times T. So that's going to be the inverse of 0.5 is 2. So ln 2 equals to K times 10.5. So K will be ln 2 divided by 10.5. Ln 2 is 0.693 divided by 10.5. It's going to be 0.066 per minute, or you can write it like that, 1 over minute. Now let's do the part B. How long does it take for 75% of the compound to decompose? It means that final concentration, that's the part B, over the initial concentration would be only 25% or 0.25. It means that A naught over A will be 4. So you have ln 4 equals to K times T. It says how long, it means that we need to look for T, and K we already calculated in the first part. So ln 4 equals to 0.066 times T. So T will be ln 4 over 0.066. So ln 4 divided by 0.066. It's going to be almost 21 minutes. So after 21 minutes, 75% of the original concentration is consumed and you have only 25% remaining. Let's see another example. H2O2 or hydrogen peroxide in aqueous phase initially at the concentration of 2.32 molar. So A naught is 2.32 molar. Is allowed to decompose. What will be the concentration at 1200 seconds? So it means that what's going to be the final concentration when time is 1200 seconds, and the K is given, which is 7.3 times 10 to the power of negative 4 per second, and it says it's first order decomposition. It must mention that, otherwise we would don't know. So we need to find out. We have the K, 7.3 times 10 to the power of negative 4 per second. We need to find out the final concentration. So we have, as we had it earlier, A equals to A naught times e to the power of negative K times T. So A will be A naught, which is 2.32 times e to the power of negative 7.3 times 10 to the power of negative 4 times 1200. So we have everything now. We can just plug in the calculator and find out the value. E First of all, I'm going to find out 7.3 times 10 to the power of negative 4 times 1200. Then you're going to say e to the power of negative 0.876 times 2.32. So that's going to be 0.966 or approximately 0.97 molar is going to be the final concentration after 1200 seconds. Again, you need to make sure that it's first order, otherwise you need to use other methods to solve it if it is not a first order reaction. Let's see another example. It says use a value of K 7.3 times 10 to the power of negative 4 per second for the first order decomposition of hydrogen peroxide aqueous solution to determine the percent H2O2 that has decomposed in the first 500 seconds after the reaction begins. So if I write the equation we already developed, it's going to be A over A naught equals to e to the power of negative KT. It says percent H2O2 that has decomposed. This A is showing the remaining concentration. You need to find out the difference, and based on that we can find out the percentage. So that's going to be e to the power of negative, K is given 7.3 times 10 to the power of negative 4. Time is given, which is 500. You need to make sure that the units match. If this one is seconds, this one is going to be 1 over second. If this one is minute, this one has to be 1 over minute. If this one is 1 over hour, this one has to be hour as well, because the whole thing is going to be unitless. Why it has to be unitless? Because here we have concentration over concentration. So both sides has to be unitless. So let's calculate this part. 500 times 7.3 times 10 to the power of negative 4. That's e to the power of negative 0.365. That's going to be 0.694. So A over A naught is going to be 0.694. It means that 1 minus 0.694 times 100% is consumed. 1 minus 0.694 times 100 is going to be 30.6% of the original hydrogen peroxide solution has already consumed, and that's going to be the final answer. I hope you enjoyed this video. I tried to have different kind of examples in dealing with first order reaction rates. Please leave me a comment if you have any question, and I get back to you as soon as possible. Please don't forget to subscribe this channel. You can have access to many other videos regarding chemistry, physics and math. Thank you for watching and have a great day.